Yes, hello students. So let us continue our discussion. Let us start with the reference electrode. So let us start with the reference electrode. So what do you mean by reference electrode? Reference electrode means no. Yes, if you want to know the electrode potential of a particular electrode, no, you need some electrode which you know the electrode potential of that particular electrode. That we generally say a reference electrode. Now, for us, no hydrogen electrode, our primary reference electrode. We conventionally taking hydrogen, this electrode potential of hydrogen as zero, so that we can measure the electrode potential of other unknown electrode. So that's what now reference electrode is all about. Yes, hydrogen is our primary reference electrode, but now for our daily practical purpose, it is observed that now this hydrogen always do not work, because now hydrogen gas has to bubble all the time and it has to maintain a constant pressure of 1 bar pressure. So that always doesn't work. That means you need some other suitable reference electrode instead hydrogen electrode. So such electrode we will call secondary electrode or subsidiary electrode. So let us discuss such electrode. First one is silver electrode. Silver silver chloride electrode. That is our one of the secondary reference electrode. Silver silver chloride, and in presence of an aqueous solution containing a common anion. So this is we already discussed in the reverse electrode section, where silver electrode is a reversible electrode with respect to the anion. So look at this. This is a reference electrode which can produce a constant electrode potential of 0.224 volt is the electrode potential of this silver electrode. So what it consists of a silver which is now in contact with the insoluble silver chloride salt, which is in contact with the aqueous solution containing a chloride ion. This is what now a silver electrode is all about, which is one of the primary secondary, which is a secondary reference electrode, and which have a electrode potential of 0.224 volt. So that's the first one. Next one is most important for you, that we will call Columnar electrode. Columnar electrode. This also we discussed. So columnar electrode is consist of a mercury which is contact with the insoluble mercurous salt. You can represent like this: Hg2Cl2, Hg2Cl2 solid, which is in actually contact with the aqueous solution of KCl. Generally we use KCl. So this is another reference electrode. So we will call Columnar electrode. Columnar electrode generally we use more. Okay. So here a mercury is contact with the insoluble mercurous salt, and which is dipped in a solution, which is in contact with the solution aqueous KCl solution. It is found that depending on the concentration of KCl, the electrode potential also varies. So it's always not depends on the concentration of KCl. For example, we give different name: desinormal columnar electrode, if the concentration of KCl is now 0.1 normal, concentration of KCl is 0.1 normal, will produce electrode potential of 0.338. 0.338 will be the will be the electrode potential of this desinormal columnar electrode. Similarly, next one, normal Columnar electrode. Normal columnar electrode which having an electrode potential of 0.2800 when the concentration of KCl solution is 1 normal. So you can see it varies 0.2800, sorry, 0.2800 volts. After that, then saturated columnar electrode. Saturated columnar electrode. Saturated columnar electrode. No, that means it has to be a saturated solution. A saturated aqueous solution of KCl which will produce a electrode potential of 0.2415. That will be the electrode potential. So columnar electrode is another reference electrode which can produce a constant electrode potential, that is depends on the concentration of the aqueous KCl solution. If it is 0.1 normal, it is 0.338 volt. If 1 normal, 0.2800. If saturated solution of KCl is used, 0.2415 is the electrode potential. So that's all now for the columnar electrode. Let us discuss the how the diagram how the columnar electrode look like. That also we can check. So keep this in mind. In columnar electrode, the electrode potential have different values depending on the concentration of the electrolyte. So here now let us represent the electrode reaction here at Z2Cl2 mercurous chloride undergo reduction to produce mercury present in the liquid state, and Cl minus will be produced. So this is the way you can represent the electrode reaction. Columnar electrode reaction you can represent like this, where mercurous chloride is converted to mercury and chloride ion. Hence now this is a reversible electrode with respect to anion. Now how the reference electrode, that's columnar electrode, look like? It consists of a glass tube in which a mercury is placed at the bottom. Mercury will be placed at the bottom. Then it consists of a paste of mercury and mercurous chloride just above a mercury and mercurous chloride at the bottom. Then aqueous solution will be filled. Aqueous solution of KCl will be filled. Then a platinum wire is inserted through a thin glass tube, which will make sure an electrical contact with the external circuit. Okay. And you have a small opening S1, where we will fill the aqueous KCl solution, and there is an opening here that we can call S2. Now which will connect to the electrode that we want to know the electrode potential. So S2, this is we call S2, which is connected to the electrode that now we want to know the electrode potential. So unknown electrode potential will be determined using this reference electrode. So this is the way you can represent a columnar electrode. The key points are what? It consists of a mercury in no, in contact with its own insoluble salt, that is mercurous chloride, in which no, an aqueous KCl solution is filled. A platinum wire, that is inert platinum wire, is inserted inside the glass tube to ensure the electrical contact with the external circuit. So, and there is a two opening is there, S1, which is through which the KCl solution is filled. S2 is another opening where no, we just connect the next electrode. So we always know required a reference electrode to find the electrode potential of this unknown electrode. So that's the way it will be. I think picture no doesn't looks good, so you can draw beautifully. So this is what reference electrode is all about. Next, Kuhn hydron electrode. Kuhn hydron electrode. Kuhn hydron electrode. Kuhn hydron electrode actually is a redox electrode which consists of equimolar mixture of quinone and hydroquinone. Quinone hydroquinone mixture. So it's based on the reduction reaction between quinone and hydroquinone. This is quinone for you. Reduction, gaining of electron in presence of acid medium, H plus ion will be there, which is in equilibrium with the hydroquinone. This is quinone, this is hydroquinone. You represent it as Q and hydroquinone as H2Q. Hydroquinone. So how can you represent this electrode? A inert electrode platinum which is in contact with the quinone and hydroquinone in an acidic solution. H plus will be there. So this is the another reference electrode, quinone hydron electrode, which is also one of the important reference electrode for you. So here two important points to remember. One is a acidic solution is required. So it's one of the acid limitation. We can say this generally works less than, if pH of the solution is less than 8, then only it will work. If the solution is alkaline, then this hydroquinone actually oxidizes. It undergo oxidation to change the equilibrium mixture between quinone and hydroquinone. And also another point, this in a alkaline solution, hydroquinone ionizes, which again changing the equilibrium mixture. That why this hydroquinone, sorry, quin hydron electrode only works in the, generally work in the acidic medium, and it should be, have to make sure it should be less than, pH should be less than 8. Okay. I think that's all to discuss about Kuhn hydron electrode. Is another reversible electrode with respect to the redox reaction, where oxidation and reduction takes place simultaneously, where quinone undergo reduction to give hydroquinone, and the equilibrium mixture between quinone and hydroquinone is what we are taking in a Kuhn hydron electrode. Okay, so that's all about reference electrode. Now let us move to the next part. Poggendorf compensation method. Okay, Poggendorf compensation method is one of the important potentiometric method which is used to measure the EMF of a cell accurately. The keywords is very important. To measure the EMF of a cell accurately, because using voltmeter also we can measure, but it doesn't always accurate. That why now this potentiometric method is more accurate, more precise we can say. So let us understand what is Poggendorf compensation method is all about. Here now we using a principle where external EMF source is applied which is greater than the unknown EMF of the cell, and now we actually making sure the external EMF actually cancels the EMF of the this unknown cell, and that point is detected using a potentiometric method. So let us discuss the circuit first. It consists of an external circuit that we represent as C, which will be the EMF should be greater than the EMF of our unknown cell. So we want to measure the EMF of a cell, which is the best method, potentiometric method, and it consists of a long wire. Let it be AB. It consists of a long wire, and A is connected to the unknown cell, let it be X, and that is connected to the galvanometer, which helps to understand the electrical deflection. And there is a movable jockey is there. Movable jockey is there now, which we use in physics, where now we can put somewhere around this AB. This is a metallic wire, long metallic wire. If you using a movable jockey, you can put jockey here, wherever you can put it. By putting that value, you can have a balancing length at which the external EMF cancels the EMF of the unknown cell. So that why this movable jockey is used here. So I will discuss that. And one more is there is a standard cell is also there. We represent it as yes. A standard cell is also is there. So this is the experimental setup for you. This is the experimental setup for this Poggendorf compensation method. It's a potentiometric method. Okay. So what's the principle? Yes, understand. This is our unknown cell. So we want to know the EMF of this particular cell. What we can do here now? A external EMF, adjustable EMF. We can change the EMF. EMF is provided, which helps to find the EMF of this unknown cell using the principle. The EMF of the unknown cell, let it be X, is always proportional to the balancing length. Let it be now, you put the jockey here, let it be D. You put the jockey here, and the length AD always proportional to the EMF of the unknown cell. So this is the point. Now you put jockey here, and this is the point where now there is galvanometer showing null deflection. There is no electric current is passing through the entire circuit, which means this is the null deflection point, or AD is the balancing length where external EMF cancels the EMF of the unknown cell. So using that principle, EX proportional to AD, EMF of the unknown cell proportional to the balancing length, that is AD. Now that's the first equation for you. Now you can reverse the key so that now this time allows the electric current to pass through the unknown cell. This time, sorry, through the standard cell. Yes, stands for standard cell. Usually Western. Yeah, let me check. It is we call Western standard cell, right? Western standard cell is used This time now we reversing the key, which means now allows the EMF to pass through the standard cell, and we adjust the jockey. Let it be this time here D dash, so that now a null deflection obtained at this length. And this EMF of this standard cell we already know, so let's keep that in mind. Let it be ES. Okay, so ES is proportional to AD dash, because this time we got the balancing length at AD dash. So let it be equation 2. So that is the balancing length at which the external EMF now balance with the EMF of the standard cell. So this is the basic principle that we use to find the EMF of the unknown cell. So EX proportional to AD. So let this 1 divided by 2. 1 divided by 2 will give you EX divided by ES will be equal to AD divided by AD dash. This is the balancing length that we can measure. So this is the EMF of the standard cell, which is now generally Western standard cell is used. Western standard cell. Now the which having an EMF of 1.018 volt. This is the EMF of the Western standard cell. So now why this is called a standard cell? Because no, it's generally we tried at different temperature, and we observed that it can produce a constant EMF around this voltage. So that why it's a standard cell. We actually represent this standard cell like this: cadmium in presence of its salt, cadmium mercury. It's a columnar electrode, right? Cadmium mercury in cadmium sulfate, it's a hydrated sulfate. Then a aqueous solution of cadmium sulfate, which is in contact with the mercurous sulfate. So that will act as a cathode, and the cadmium act as an anode. Hg2SO4, mercurous sulfate in contact with mercury. Mercurous sulfate in contact with the mercury. So that's all about now the representation of Western standard cell. It consists of cadmium in cadmium sulfate, aqueous solution of cadmium sulfate solution in contact with the cathode will be mercurous sulfate and mercury. That will be the cathode. So that is the standard cell. Using the standard cell and an external EMF source, we can find the EMF of an unknown cell accurately. The principle is nothing but at the point where no external EMF cancels the EMF of the unknown cell, you can find the balancing length. So EMF of the unknown cell will be always proportional to the balancing length in the potentiometer. So that's the basic principle for you. EX by ES will give you AD by AD dash, which again I am repeating, this potentiometric method will give you more accurate result if you want to find the EMF of the cell, where now voltmeter actually generally changes the concentration of the electrolyte, which varies the our EMF of the cell as well. So which means now voltmeter, yes, for a simple purpose we can use, but if you want to measure the EMF of a cell accurately, go for potentiometric method. So that's all about the Poggendorf compensation method. Okay. So next class we can discuss the thermodynamics of cell reaction. Okay. Thanks for listening. Let us find out.